Welcome to this explainer on fluid mechanics. If you're a mechanical engineering student, or honestly, just someone fascinated by how the physical world works, you are in the exact right place. Today, we're going to meticulously build your foundational engineering toolkit. We'll start from the absolute basic definitions of matter, work our way through fluid properties, and then cap the whole thing off with the highly satisfying step-by-step numerical solution. Let's get to it.
Here is our roadmap for today. We'll cover an introduction to fluids, fundamental properties, viscosity and fluid types, Pascal's law and hydrostatics, and finally, solving a fluid problem.
Section 1. Introduction to fluids.
Simply put, a fluid is just defined as any substance that can flow. But, in engineering terms, we have to be a bit more precise than that. A fluid is a substance that deforms continuously when it's subjected to an external shearing force. Unlike a solid, which resists deformation and holds a rigid shape, a fluid just keeps on yielding and flowing no matter how small that applied shear force is. And remember, this encompasses both the liquid and gaseous states of matter.
Now, because fluids are so incredibly dynamic, we actually have to break the mechanics, the study of the forces, down into three distinct branches just to analyze them properly. First, there's fluid statics, which is the study of fluids completely at rest. Second is fluid kinematics, where we study fluids in motion, but, and this is key, we completely ignore the forces causing that motion. And finally, fluid dynamics, where we look at fluids in motion while actively considering those driving forces.
Section 2. Fundamental properties.
All right, these three definitions are our absolute core foundations. First up is density, or mass density, which we denote with the Greek letter rho. It's simply mass per unit volume, typically expressed as kilograms per cubic meter. Next is specific weight, or weight density. So instead of mass, it's the weight of the substance per unit volume, mathematically equivalent to density times gravity, or rho times g. Finally, we have specific volume. This is literally just the inverse of density. It's the volume occupied by a unit mass of a fluid, measured in cubic meters per kilogram.
Building right on those foundations, we get specific gravity. This is an incredibly useful ratio, usually denoted by S, which compares the specific weight of our target liquid directly to the specific weight of a standard liquid. For liquids, that standard is almost always just pure water. So it's a quick, unitless number that instantly tells us if our fluid is heavier or lighter than water. Pretty handy, right?
Section 3. Viscosity and fluid types.
Okay, think of viscosity as the internal friction of the fluid itself. It is the exact property that dictates why honey pours so much slower than, say, a glass of water. As the fluid layers slide over one another, viscosity is the resistance they offer against that shear force.
We can actually mathematically define this friction using Newton's law of viscosity. This law basically states that the shear stress on a fluid layer, which we denote with tau, is directly proportional to the rate of shear strain, or the velocity gradient, du over dy. The constant of proportionality that turns this relationship into a workable equation is mu, which is our dynamic viscosity.
But engineering is all about practical application, right? So if we take that dynamic viscosity, mu, and divide it by the fluid's mass density, rho, we get what is known as kinematic viscosity, denoted by nu. This essentially tells us how a fluid's inherent resistance to flow interacts with its own mass. That's absolutely vital when you're doing things like sizing pipes or pumps. It's typically measured in meters squared per second, or traditionally in a unit called Stokes.
So, the crucial takeaway here is that in the real world, fluids are categorized entirely by whether they obey this law. Fluids that perfectly follow Newton's law of viscosity, meaning their viscosity remains constant regardless of the shear stress you apply to them, are called Newtonian fluids. Water, air, and petrol are great examples. But then we have the rebels, non-Newtonian fluids, which absolutely do not follow the rules.
These non-Newtonian fluids exhibit some fascinating, honestly almost counterintuitive behaviors in the real world. We break them down into a few main types. First, pseudoplastic fluids, like blood or ketchup. These are shear thinning. The harder you push them, the thinner and runnier they get, which, by the way, is exactly why you have to smack the bottom of a ketchup bottle. Then we have dilatant fluids, like wet sand. These are shear thickening. They actually lock up and get thicker when you apply force. Finally, plastic fluids, like toothpaste or mud, act kind of like a solid and require an initial yield stress, a strong push, just to start flowing at all.
Section 4. Pascal's law and hydrostatics. To prove these fluid pressure concepts, I want you to imagine mapping out the forces acting on a tiny, static 3D block of fluid. By setting the sum of those forces to 0 in the x, y, and z directions, because remember, the fluid is at rest, we can see exactly how pressure distributes. The math here proves that the pressure in the x direction equals the pressure in the z direction, and the pressure in the y direction also equals the pressure in the z direction.
The elegant mathematical conclusion of that derivation gives us Pascal's law. This is a massive foundational rule of fluid statics, assuring us that the intensity of pressure at a single point inside a stationary fluid acts completely equally in every single direction. It literally doesn't matter if you measure up, down, or sideways. At that specific microscopic point, the pressure is perfectly identical.
Now, by applying our force balance concepts to a vertical column of fluid instead of just a single point, we uncover a really vital rule about depth, the basic hydrostatic equation. This derivation reveals that the rate of increase of pressure in the vertical, downward direction is exactly equal to the local specific weight of that fluid. Simply put, the deeper you go, the more pressure you feel, and that increase is directly proportional to how heavy the fluid is.
Section 5. Solving a fluid problem. Let's put this all together.
All right, here is our mystery to solve, straight from the source material. Imagine we have exactly 1 liter of oil, and it weighs 8 newtons. From just those 2 pieces of information, how do we find its specific weight, its mass density, and its specific volume? Let's dive in and see how the toolkit works.
We can deductively contour this in 4 logical steps. First, we absolutely must standardize our units by converting liters to cubic meters. Then we chain our fundamental formulas together. We'll find specific weight by dividing weight by volume, we'll find mass density by dividing that specific weight by gravity, and finally, we'll find specific volume by just taking the inverse of the density. Let's run the numbers. First up, volume. 1 liter is mathematically equal to 10 to the negative third cubic meters. That's step 1 done. For step 2, our formula for a specific weight, little w, is total weight divided by volume. So we divide the 8 Newton weight by 10 to the negative third cubic meters. This yields a specific weight of precisely 8,000 newtons per cubic meter.
Moving right along to step 3, we know specific weight equals density times gravity. So to isolate density, or rho, we take that 8,000 specific weight we just found and divide it by standard gravity, which is 9.81 meters per second squared. Doing the math, we successfully reveal the mass density of this oil to be exactly 815.49 kilograms per cubic meter. Finally, step 4. We need the specific volume, which is just the volume per unit mass. And, as we learned earlier, this is simply the inverse of our density. So we divide 1 by our new density of 815.49. This gives us our final answer, a specific volume of 1.226 times 10 to the negative third cubic meters per kilogram. And boom! Just like that, we've perfectly completed the problem and proven that our foundational engineering toolkit absolutely works in practice.
So you've officially mastered fluid statics and properties today. You've got the formulas, you know the laws, and you can comfortably run the calculations. But this leaves us with a pretty provocative thought to explore next time. If we can calculate everything so perfectly and predictably when a fluid is at rest, what happens to these forces and this math, the exact moment the fluid is unleashed into rapid, chaotic motion? Thank you so much for joining me on this explainer, and keep that question bouncing around in your head until we tackle fluid dynamics.